So Internet Protocol v4 is long in the tooth for sure. So we now have, and have had for the last several years, although you wouldn't really know it, a next generation IP stack, the IP version 6, that was finalized in Request for Comments 1883 and 1996. Check the course notes because I give you all the RFC links. They're freely downloadable, you don't have to pay for them, and they're also written in non-technical language. IPv6 is meant to solve the address depletion of IPv4 because IPv6 addresses are a whopping 128 bits long. That's 5 times 10 to the 28th. That's 5 with 28 zeros after it, addresses for every person on Earth. So again, with technology, you think today, oh, we'll never reach that limit. You know we will, but hopefully it's going to take us a long time. Some other things that have been corrected in IPv6 that were problematic or are problematic in IPv4 are that the header structure in IPv6 is a lot simpler. There's no broadcast with IPv6. v4 tends to be pretty chatty and tends to put a lot of network pressure on a network. You don't get that with IPv6. There's also built-in encryption, and most importantly, IPv6 is built to coexist with IPv4. I'll bet you use IPv6 every day and you don't even know it. The address format for IPv6 is pretty intimidating, I have to be honest. Again, we turn to hexadecimal because these 128-bit addresses are absolutely huge. By default, the 128-bit hexadecimal address is broken in two, with the first 64 bits denoting the network and the second 64 bits for a node. Now notice that that 64-bit node section is twice as long as binary. It's actually much more than twice the number if you do the math. But in terms of bit length, it's doubling the bit length of IPv4. Specifically, an IPv6 address consists of 8 groups of 4 hex digits, with each group representing 16 bits, or 2 octets in IPv4 language. You can drop leading zeros. You can do a couple different things on making IPv6's addresses a little easier to manage. And DHCP is a network service called Dynamic Host Configuration Protocol that's meant to simplify the distribution of IP addresses. So you think with IPv6, these honkin' long addresses, any help you can get to accurately deploy IPv6 addresses is going to help, and that's definitely true. Here's some examples. The quad A refers to how IPv6 addresses are represented in the domain name system, or DNS. We'll talk about DNS at another time. But you see it right. We have an IPv6 address. This is a public address, globally routable, and you're thinking, my word, how can I write this down? If somebody says, what's your IP address? Am I supposed to remember this? There are some tricks. You can compress all of the contiguous zeros and represent that as double colon. You also can strip away leading zeros, which leads to a little bit more compact. But yeah, no doubt about it, IPv6 addresses are pretty gnarly looking. Moreover, with IPv6 addresses, another thing that helps not having to know those long numbers is SLAC, or Stateless Address Auto Configuration. By default, any IPv6 capable system is going to auto-generate a link local address that starts with FE80. Know that for your exam. So an FE80 address is going to allow hosts, in the example at left, on one network segment, they can communicate with each other just fine. But these link local addresses are not going to pass through a router, and so therefore a host from the top network segment is not going to be able to communicate with one on the bottom, and vice versa, using just those link local addresses. The loopback diagnostic address in IPv6 is ::1. Again, know that for your A+, just in case CompTIA asks you.